We will be talking about coherent states and solids. Now, quantum mechanics has been puzzling to physicists ever since it was created. One of its most non-intuitive features is the inability to measure the position and momentum of a particle simultaneously with certainty. Look at this classical ball rolling. According to classical mechanics, I can precisely specify its position and momentum at a certain instant of time. In quantum mechanics, these two quantities get promoted to operators, with each essentially being a Fourier transform of the other. What it means is that if we try to measure the position certainly, then the measurement of momentum gets dispersed over all space. And if we try to measure the momentum certainly, then the measurement of position gets dispersed over all space. A relation captured by the famous Heisenberg uncertainty principle. This is so non-intuitive that Schrödinger, one of the founders of quantum mechanics, apologized for being a part of its birth. So being an apologetic man, he tried to construct the most classical quantum state. For that, he chose the favorite system of physicists, a harmonic oscillator, but well, the quantum one. Equipped with the Hamiltonian and the eigenstates, we can define operators called ladder operators and write position and momentum operators in terms of them. The dagger operator gives one state above, whereas the annihilation operator gives one state below. We can also define a number operator in this manner with the following commutation relations. Using these relations, we can rewrite our Hamiltonian in terms of the number operator, and we can also rewrite the nth eigenstate as n creation operators applied to the vacuum state. This now leads to the question, what happens when you annihilate the vacuum? We take the answer to be 0. This answer serves as the basis for our definition of a coherent state, as we define a coherent state as an eigenstate of the annihilation operator. Doing a few calculations as in the paper, we find that such a state must look like this. Following up with more calculations, we can show that for such a state, the uncertainty principle is saturated. This means that we can determine the position and momentum with almost equal and maximal accuracy. Using group theoretic methods, we can show that the space of coherent states is symplectomorphic to the complex line, with the connection given by alpha equals q plus ip by root 2. This also means that for a state alpha, the position probability density peaks at q, as can be seen, and the momentum one at p, as can be seen. Thus, we are actually working with a most classical quantum state. We can also define a coherent state as the result of a displacement operator displacing the vacuum to some other point on the Argand plane. This is experimentally done using an external field, and the stronger the field, the more the displacement, so the norm of alpha is proportional to the field strength. This action can be viewed as a translation of the origin as displayed in this, well, horribly made animation. Well, a harmonic oscillator seems fun, but what part does it play in the bigger picture? The answer lies in quantum field theory. As the most successful theory in physics yet, it says that our universe is covered by fields whose discrete excitation gives you particles. So for example, the excitations in the electromagnetic field gives you photons. We can mathematically quantize this field and obtain a Lagrangian and Hamiltonian density for it. And we find that the Hamiltonian comes out to be the sum of lots of quantum harmonic oscillators Hamiltonians, each in a mode k. This gives a way of defining coherent states for this field, aka macroscopic coherent states, using that of a harmonic oscillators one. Here also you have the ladder operators, and the annihilation operator just kind of bursts the excitations. So a coherent state is a state in this field which is, well, unaffected by the bursting. We can now look at the utility of such states throughout physics. For that, we first need to answer the question, why coherent? To answer this, we define a phase operator akin to the number operator. Note that defining a phase operator has been a challenge for a really long time, and we are considering the most successful of those propositions, the PB phase operator. Now to draw the contrast properly, we first consider the number states. In this basis, the expectation value of number operator gives the mean photon number with zero variance. The result for the phase operator, however, matches a classical uniform probability distribution between theta naught and 2 pi plus theta naught. So you can count the number of photons for such a state but make no sense of a phase. This is akin to a crowd moving around a street but with blocked walls. The number remains constant, well, you can count them if you want to, but everyone is doing their own thing, so there is no well-defined phase. SQM is a statistical theory the expectation is just the mean across an ensemble. But since the variance of n is 0, it means that all measurements will yield the same value of photon number. We now consider the coherent state basis. If you write alpha as r times e power ik, then for a highly excited coherent state, that is for a large value of r, the expectation value of phase operator gives the phase, with its variance being very low. For the number operator, we get an equal mean and variance, both being proportional to mod alpha squared. This is a sign of a Poissonian distribution. This means that all measurements are statistically independent, and hence for high field strength, well, approximating expectation of n to be infinite, we can make sense of a state being unaffected by an annihilation. This is akin to a dance in which number of dancers keeps on changing, but they are dancing in a phase. This assumes indefinite amount of dancers behind every dancer you can see. So their number is not well defined, but the phase is. Again, to make these observations, we have to consider an ensemble and take the mean and variance across it. We can also see that the relative dispersion is inversely proportional to the field strength. So for highly excited coherent states, the output is a very thin beam. This can be seen beautifully in a laser, where the states are coherent and highly excited. So they have the same phase almost, and hence a single frequency. For such a state, the expectation value of n is more or less infinite, and you can see from the formula of intensity why lasers are so powerful. To define coherent states in solids, we restrict ourselves to only the first band and for now only 1D. We first construct the analogues of position and momentum operators for one band in the first Brillouin zone and then extend it throughout the lattice. Note that in general, a solid has many bands, but a lot of interesting physics takes place in the first one and hence the restriction. We work in the momentum space, so the crystal momentum operator gives us a straightforward operator with eigenstates as delta functions at a given k prime. As the system is translationally invariant, the delta function must be at all the points with separation 2 pi by a from the given one. We now construct the position analog, which must be consistent with Bloch theorem. Just like in canonical quantum mechanics, x is ih cross dou by dou p, we take r to be ih cross dou by dou k. This should have eigenstates localized at lattice points. Those functions are essentially Fourier transforms of the Bloch functions and are called Wannier functions. This is alright if we stay within the first unit cell, but a problem arises during the extension to entire lattice. You see, we can multiply an arbitrary phase to a Bloch wave function and it will still remain the same, but this drastically changes the form of the Wannier function. This turns out to be a blessing in disguise as we choose a phase which gives us maximally localized Wannier functions. So our operator now has such properties, and for the first unit cell we essentially have these as the eigenstates. Here is a representation of how these states look like. Defining a coherent state is now a trivial task. We just replace x by a nu and p by k to get such a state in momentum representation. We can actually quantize the phonon field and define coherent states the way too, but that doesn't turn out to be very useful. This is because we don't have a mechanism for selectively picking out phonon modes. Since phonons are basically lattice vibrations, the highly dissipative environment makes it even more difficult to use their coherent states. However, coherent states find a very powerful application in superconductivity using off-diagonal long-range orders concept. Writing the one pair density function and for large separations how it looks like, we take if the states were number states, then these quantities would vanish, but this is not so if and only if the states are coherent. For k0, the macroscopic occupation or the order parameter looks like this, with an arbitrary but a constant phase. ODLRO is needed to form Cooper pairs. An electron flows through the lattice and distorts it as it does. This distortion creates a small positive concentration to which the other electron gets attracted to. So the first one kind of drags the second one along. This pair formation cannot take place if the states were not coherent. These pairs at the end entangle and then move as if they were passing through no resistance at all, giving rise to superconductivity. The coherent states in solid also have a potential application of explaining the quantum mechanics of resonance. So if we apply a wave with the natural frequency of glass to it, then it breaks. What possibly might be happening is that the phonons we apply form a coherent state in the acoustic band of the glass. For such a state, as number is ill-defined, what we have are a huge number of vibrations in the same mode. This ends up breaking the glass. This also suggests that there exists a natural frequency for every band. It provides further research questions that I would definitely be pursuing. Coherent states are crucial to the subject, and the possibility that something as well known as resonance is something as unknown as a phononic laser excites me. Thank you.